Hello everyone. For the last few sessions, we learned how to program any digital circuit by three styles of abstraction. Apart from it, there are some more things which have to be focused to become a good Verilog designer. Today's agenda is to know what are the tasks and functions and their significance in the hardware description language, in fact, Verilog. A designer is frequently required to implement sometimes the same functionality at many places in a design. The design may be any kind of abstraction we can use to develop the design. So the most commonly used part, they are abstracted into a routine or a subroutine or a procedure, and these routines are invoked instead of repeating the same number of instructions many a times. So we call the process of grouping the number of instructions, in fact maybe a routine or a procedure, we call in our Verilog HDL as in terms of a task and functions. So in a C language, a function is nothing but a group of statements that are always together to achieve a task, specific task. In our hardware programming language also, it supports encapsulating, that means putting together a piece of code which we call it as a task or a function that is invoked from different parts of your design. So the specialty of task and functions in our Verilog HDL is it allows the designer, that means the designer can able to abstract the Verilog code and he can use this abstracted code at many places in the design. So these tasks and functions are employed in mainly in behavioral abstraction, and they are always defined in a module, and these are local to the module. But only the difference is in our C language, whenever apart from the main function we are going to write any customized function, we use it to follow a function declaration, and the function call will be present inside your main function, and the definition of your customized function is written outside of your main function. But coming to here, the task and functions, the definition of them are always provided within the module itself, and they are local to the module. Okay, apart from that, this task and function provides the same purpose as how we do have the subroutines in our software programming languages. The main advantage of using the task and function is the readability becomes very easier, and for code management purpose also. Okay, so the task and functions mainly they do not contain any always or initial statements, but they always called from always block or initial blocks. And one more thing we need to be clear on the task and functions are task contains always a delay, timing or event control constructs, but a function will not contain any of the same. And the functions are mainly used for combinational realizations which have always a zero simulation time for its execution, and it provides exactly an output, one output only, a function. So these are the some of the characteristics of the task and functions. We in detail discuss about them in the further slides. So coming to here, the task The tasks are always declared with the keywords task and task. That means so whenever we, as I have said you that task and functions whose definition is always present inside your module. So this task and function always begins with task and ends with end task as the keywords. And these tasks are having inputs and outputs and in-out arguments, and they are declared implicitly as a registers. Okay, I will explain you the second point whenever I am like giving you the example of a task Verilog program. As we know that a module will be having inputs and outputs ports, and these ports are normally they will be interacted with the environment signals. Like ports are used to connect external signals. These external signals are nothing but these are the signals which are present in the environment, and this environment generally wraps the module. Similarly, that means inside the environment I am having a module, and inside my module I am having a task block. So for the module I will be having an input output ports. For the task block I will be having input output or in-out arguments, such that the in-out arguments in the task are used to pass values to and from the task. Like I can able to like elaborate in this manner. Input arguments are processed in the task block. Output argument values are passed back to the variables in the task invocation statement. I will explain you this statement once again by having an example, and before it let me introduce you what is the task invocation syntax and declaration syntax. So I will be having in this format, this is my task name, and the task may also have some arguments during the time of invocation, and during the time of task definition or declaration the syntax is in this manner. That means task name, IO declarations, and if any variables or events are present they are also have to be declared in the task block, and many number of statements are present means I definitely have to use begin end keywords. After successfully completing the processing of something there will be end task. That means I have completed the task. So this is the best example what I can give for the good explanation of the usage of task and functions, sorry, for the task. So here I am having a module name, and the name of the module is exp task. So this module, inside the module I am having here a task block. So outside the module I am having an environment that is nothing but a test bench. Generally you know that the test bench is generating some signals and it is checking the functionality of a module. That means it is passing the signals through the input port, and it is observing the functionality of the module through the output ports. So this IO declaration use generally the keywords input, output or in-out for your task. Based on the type of argument declared, the input argument or the in-out argument are passed to the task into the task, and the input arguments are processed. We are going to get the output argument, and this output argument are again passed back to the variables in the task invocation statement. So let me have here, I am having the module name module exp task, and this module is having input ports as well as the output ports. P comma Q are the input ports, K L M are the output ports. So these each and every port is of 4-bit in width. Okay, So always I am depending on P comma Q. That means always I am dependent on my inputs. Now begin end. So like in the always block, as I have mentioned you that the task or functions are always called from always block or initial block, but we shouldn't use any always or initial inside the task. We shouldn't use here. That means the task and functions are always called from the always block. So all from the always block is calling a task. What is the task here? Bitwise operation, and the arguments will be present here. So what is the order of arguments that I am maintaining here? The same order I need to be used during the time of task declaration, like KLM. These are the outputs I have used, next followed with inputs. In the same manner, during the time of task declaration, the same order I will be following. So always block is calling a task. So the task definition should be present inside the module. That means like before end module only I need to complete the definition of my task. So task name. What is the task name here? Bitwise offer. Bitwise offer is the task name, and output or input declaration. So whatever the order that I am followed here, the same thing I will be following here. Output read down to 0, input read down to 0, a comma b, xyz. So you might wonder, sir, you have taken here pqklm. These are your input output ports for the module, and you have used some other different name for your arguments in your task. Why like that? The thing is, it is completely my flexibility. Okay, so like ports generally, as I have mentioned you that excuse me. So here the input values passed to the task here are A and B. That means here the input values passed to the task are A and B. But generally, like you can able to see here, as I have given P comma Q, these are the input ports present in your module, and this small a and small b are nothing but the arguments. These are nothing but the arguments present in the task. That means here what is happening, the input values are passed to the task are P and Q. So this is my task. The input values are passed to the task are P and Q. That means small a equal to capital P and small b equal to capital Q. And once again I am repeating the statement. The input values are passed to the task are capital P and capital Q. When the task is entered, that means A equal to capital P, B equal to capital Q. The three output values are computed. What are the output values here? KLM. These are the output values are completed. So immediately the task may not give the result. It generally or certainly takes certain amount of time to produce the output. So I have here used XYZ. This XYZ is nothing but it is producing some values, and these values are handed over to KLM, which are nothing but your output ports of your module. So that means here you can able to see when the task is completed, the output values which are produced by XYZ are passed back to the calling output arguments. So these KLM are nothing but here the calling output arguments. Therefore, I can say that now XYZ is handing over its value to your KLM output ports. So that means whenever a task is entered, P is given to A and Q is given to B, and some processing will be happening in the task block. as soon as the values are getting evaluated in the form of xyz, this xyz will be handing over to the the calculated value to klm output arguments, or the, because klm is nothing but here these bitwise offer in the task name bitwise offer, these are in the form of an argument klm. In this manner we can able to realize how a task is used in our Verilog HDL behavioral abstraction modeling. Let me take one more example for the task. So here I am having a module name that is collections, and I have taken a variable that is kgf, which is of type integer, and initial always two blocks I have used here, initial, and the task name is first week, and always the task name I have used here is different weeks. So once I am calling the task means definitely I need to provide its definition. So task definition is first week here, and task different weeks definition, task task name. So let me complete the definition of first week task. So begin end. So after the after end of first week, what are the collections? So hash 1, what are the collections of kgf movie, that is 98 crores. Okay, completed. Begin end, I may use or I may not use, because as I have here one statement, there is no certain there is no that much necessity to use begin end keywords. Next, task different weeks, because different weeks is nothing but it is the task name. So let me complete the definition of my task name here, begin end, because I am having many number of statements. So after the end of second week, what are the collections of kgf movie? 43. And after the end of third week, it is 23. And after the end of fourth week, 10 crores. After the end of fifth week, it is 5 crores. So these are the box office collections for your kgf movie in so and so weeks. So complete once the task definition is completed, you need to come out of the task block by end task, next end module. So this is one of the example I can give for the task. Okay, so next one we need to discuss is about functions. These functions are generally declared with keywords function and end function. So before discussing about a function, yeah, let me complete the discussion, and after that we will be having some difference chat on task and functions. There I can provide you one more good example on how to differentiate a task and function in the practical world. Okay, so these functions are nothing they will be starting with the function name, and if the function definition is completed, we are going to use the keyword end function. They generally doesn't have any timing or delay or event control construct as how do you have for the task block. And as you know that in the task block you may have an input argument, output arguments, as well as in-out arguments, but in the function you only have one input argument. There won't be any output or in-out argument during the time of function declarations. And so when a function is declared, what, okay, so let me go with one example of a function, and later I will explain all these points. So this is how a function can be invoked. This is function invocation syntax, that is function, or if present arguments are present, they are declared in this manner. So this is function declaration syntax, function name, and there will be some input declarations. There won't be any output or in-out declarations, and if variables are present, they can also be declared here, and begin and end function. So you can see here, Okay, let me have this example. So module test is my module name, input and outputs, function adder. So actually I need to write assign, inputs are a and b, output is c. Here the module, what its job is, assign c equal to adder of a comma b. That means here adder, it is a function name. So function name, that means we are calling the function with arguments. So let me complete the definition of a function here. Function adder, inputs are a comma b, and whatever the function name that I am using here, the same the function name or function identifier whatever I am using here, the same thing I will be using in the function definition or the function declaration. So adder equal to a plus b. Okay, so you what it is nothing but function is returning something. So the function block is returning something adder, and that is again given to your C, which is nothing but your output port of your module. Okay, so what is happening inside it, let me take this as an example. So when the function is declared, for example, here calc parity is nothing but my function. So this is my function name with argument. So during the time of function declaration, a register that is calc parity I have used here with the same name of my function. So what is my function name? It is calc parity. It is nothing but my function name or function identifier, and this calc parity is equal to XOR of address. So a register with name function identifier is declared implicitly inside my Verilog. So am I providing exclusively what is this calc parity? That means what is its type, have I mentioned here in my function declaration? Never, I never mentioned here what is its type, calc parity type. Okay, so this function is returning calc parity value. Okay, this calc parity is handing over its value to parity, but parity is of type rich. I have declared in my module declaration. During the time of my module declaration, I mean, IO port declaration of my module, this parity is exclusively defined or declared as of type reg. But that means calc parity I didn't mention anywhere. I didn't discuss what is its type, right? But parity type I have mentioned in the module. That means here what is happening, if parity is a register, definitely calc parity is also a register, right? Because calc parity is handing over something to some variable. That means this variable is handing over something to this variable, means if this variable is a register, this might be also a register. So that means this calc parity is a function name, and this function name or the function identifier I have used in the function definition or the declaration. That means here, that means can I call this calc parity indirectly as a register which is declared implicitly. I haven't used any exclusive declaration of its type. That means it is declared as a register implicitly. So the output of this function, that is calc parity, is passed back by setting the value. So I will be having the value, and this value is passed back, and here the value is passed to this parity, and so we know that what is this parity, again it is of register function. Okay, so it is of again register function. That means whatever the thing we have calculated here, it is passed again back to your parity, and this calc parity is implicitly declared as a register inside my Verilog HDL code. So here the function, whatever it is, yeah, the function calc parity is invoked like this, and it is declared here in this manner with some input arguments. So as soon as like the function definition block is completed or the function is getting executed, the return value is placed here, that means calc parity, and it is handed over to the parity register. So as it was invoked here, the calc parity is invoked here. In this manner we can able to analyze what a function like how a function can be used in our Verilog HTML language. So I do have here one more example for the function. So you can able to see a web series I have taken. The module name is Money Heist, and I am having here three variables, that is Tokyo, Nairobi, and Rakul, are of 3-bit vector quantities, and these are of type register. And I have used three more variable names, that is Rio, Helsinki, and Professor, which are of scalar quantities. Okay, so just leave this block, initial begin. Now always I am depending on certain inputs because I have considered these three as my inputs. So Tokyo, Nairobi, and Rakul, which are of 3-bit vectors. Like Tokyo may be of 4-bit binary 1011. Nairobi may be a 4-bit binary 0101, comma, and the last one, that is Rakul, as 4-bit binary 1010, like this. Okay, so as Tokyo, Nairobi, and Rakul are of 4-bit vectors. Now begin Rio equal to and reduction, that means it is the function name. So this function name with an argument, what is the input argument for this and reduction function name? Tokyo. So this is my function call, and the function definition or the function declaration should be within the module itself. So function name. So function name with input argument. What is the input argument I am having? Tokyo. So I can use some other like whenever it is Tokyo is entering into the function block, it may have like certainly some other different name. So input read down to 0, I have used it here t as its argument, function argument. This is my input port and this is my input argument of the function. So input read down to 0 t begin and reduction. So what is the function identifier of the function name I am using here? An implicit register it is actually. So, an implicit register declaration is done for and reduction. So because Rio is defined or declared, it is of register, that is a scalar register. So and reduction, now I am doing a bitwise reduction for t. That means Tokyo, which is a 4-bit binary 1011, this Tokyo is handing over its value to small t. This is nothing but an argument for your function. So this input argument is having a value now 4-bit binary 1011, and I am doing here and reduction, that means bitwise reduction I am doing here. So that is nothing but and I need to change the symbol and t. So 4-bit binary 1011, 1 and 0, like this it will be 1 and 0 and 1 and 1. So what will be the result for it? Certainly it will be 0. So that means this function produces something, that is at the end of the function execution I will be having some value, and the return value is placed where the function was invoked. As the function got invoked here, you can able to see the function got invoked here, the return value is placed in this Rio register. What is the operation it is doing? It is performing bitwise and reduction, sorry, bitwise operation, not, it is a reduction operation, and reduction operation it is performing. So Rio is performing and reduction operation. I mean Rio is holding the value that is returned by the function, that is and reduction. Similarly, I will be having Helsinki, one more scalar register, and it is holding the value which is generated by the return value of this function, that is OR reduction, and this is performing OR operation, that is reduction OR operation, it is performing. And one more register I am having, that is professor, and this professor is performing XOR of, for which one? Rakul because it is also a 4-bit vector. So this Rakul is handing over its value to whom? R, which is again input argument for your function block. Read down to 0, and so here it should be XOR reduction, because what is the function name I am using here, the same name should be replicated here also. And here R means I need to use R. So in this manner we can able to analyze how a function is used in your Verilog HDL program. Okay, so let me come back here. Hence completed the task and functions example. So you might found here during the time of task example, you might have seen some delays. That means a delay or an event control construct is present, right? But in the function you didn't encounter any event or any delay control or any event control construct in your Verilog HDL program. So the practical example for a task and a function is, for example, if a lecturer is entering into any classroom to take any subject or any lesson, immediately as soon as the lecturer has entered into the classroom, immediately the students action is they will be standing and greeting the lecturer. So that means the students functionality is to acknowledge to lecturer or the teacher as soon as he is entering into the classroom. That means it is the functionality of the students. So the functionality of the student means the function execution has done in 0 simulation time. That means as soon as the teacher entered into the classroom, the students had stood and greeted. That means without any delay they have done their functionality. That means to greet the teacher. So what is the task here? So task is nothing but, if the teacher had given some assignment work to the students, the student generally consumes certain amount of time to complete the execution of the assignment. That means the student may consume 1 day or 2 days, certain amount of delay they definitely will take and will return back the work to the teacher. Okay, now this is the best example in order to differentiate a task and a function. So for the function and task differences chart we can able to see here. And coming to the first one, a function can enable another function but it not enable any task. Like as soon as the first bench students have stood and started greeting their teacher, means definitely the back row students also will stand and greet the teacher in order to complete their functionality. That means the functionality of the first bench, like as soon as the first bench students have executed their functionality, immediately the next bench students also will start executing their own functionalities. So here a function is invoking some other functions. or a function of the first bench students is invoking or calling the functionality of the second bench students or the latter bench students. So in this manner. So coming to task here, a task can enable other tasks and functions. So like if a teacher had assigned some assignment work to a student, the student himself can complete the assignment work, or he can hand over the duty of completing the assignment work to his juniors also. That means a task which is assigned to a student, the student invokes some other student to perform that task. In this manner it goes. So it generally takes non-zero simulation time. And coming to function, it doesn't have any delay event control constructs. Tasks certainly have all these delay event timing control construct. And a function is having input during the time of its declaration. It doesn't have any output or in-out arguments during the time of declaration, and it always returns a single value after its execution. Coming to task, the task block will be having input, output as well as the in-out arguments. It doesn't generally return any value, but whatever the values that are calculated or performed or processed, those values are passed through the output or the in-out arguments back to the output ports. Okay, in this manner it goes. So like you can able to see here, task and functions are mainly used in our behavioral abstraction, and functions are always used for combinational realization that always executes in zero simulation time, and provides always a return value. So this is a brief description about the task and functions. Thank you for the day.